Cool. I think anyone else that joins can just catch up in another way. So welcome everyone. It's great to have you all here. My name's Rob, and I'm currently studying towards my bachelor's in computer science at the University of London, like many of you probably also are. I also work full-time as a backend engineer at Message AI. We're an outreach intelligence startup that employs machine learning to make the task of writing email copy easier and more successful. We use Go for our microservices, and I write Go at work daily. So today I'm here on behalf of the University of London's chapter of the Google Developer Student Club, and I'll be giving you an overview of the language and of some of the things that I think make it special. So before we start, I'd like to mention a bit more about our club. We're part of the greater Google Developer Student Club system, and our chapter represents the University of London. Google Developer Student Clubs are community groups for college and university students interested in Google developer technologies. Students from all undergraduate or graduate programs with an interest in growing as a developer are welcome to join. And by joining, the students will be able to grow their knowledge in a peer-to-peer learning environment and sometimes build solutions for businesses and communities. However, since University of London is a distance university, in-person events are pretty impractical. We try to make up for it by having virtual events like this one today. So if this sounds interesting to you, don't hesitate to join us if you haven't already on the link shown in the slide. We have presences on Discord and Slack where you can also engage with our community and learn about upcoming events. Today's topic is Go, and I'd like to tell you a bit about the history of the language, why it was made, and what it's turned into. Following the intro, we'll see a bit of some reasons why a developer might want to use Go for their work and how it makes our work as developers easier. And then after that, we'll explore some parts of the Go tour together, and we'll highlight some standout features. I'll also give some content from other sources where appropriate to give you a more complete picture of the language. And then finally, we'll build some example applications somewhat live. And for that, we actually have a companion GitHub repository, which I encourage you to check out after the talk if you want to refer back to anything that we've built. So yeah, now I'd like to give credit to the official Go tour. This presentation uses their resources quite extensively, and throughout the presentation and on the GitHub, we have links to the Go tour and other resources that we've used. And the Go tour specifically is a great resource for beginner Go programmers, since it really describes key features of the language and provides examples and even a way to run these examples in a built-in code playground. So definitely check that out. On to a bit more about the who, what, when, and where of Go. So the creators of Go set out initially to create a language which brought along many of the features that developers would be familiar with from other languages already. And what they wanted to do was combine the features that they believed were the most influential to aid the development of high quality and simple software. So what crystallized from their development process was a C-like language with similar static typing and runtime efficiency, but coupled with the ease of readability and usability of languages like Python or JavaScript, while still maintaining high performance networking and multiprocessing features. So the development started at Google in 2007, and it was started actually to address some of their direct problems. So modern software development in the industry is quite complicated. And since developers are essentially knowledge workers at the end of the day, complexity like this can really affect our productivity and our ease of use. And large software companies like Google really understood that this can directly affect their bottom line, since developers being engaged in longer development cycles, having to invest large times in building and optimizing and deploying their software can often lead to unexpected delays or subpar output from the developers. So Google at that time brought together some of the foremost computer science experts to create a new open source language invented particularly to deal with these problems in the cloud native environment, which was emerging at that time. So the three creators of Go brought some varied experiences with them. Rob Pike is known for his time at Bell Labs, working on the initial release of Unix and some related systems. Ken Thompson, who's also from Bell Labs, is credited with leading the effort to create Unix, and he actually also created the predecessor of the C language, B. And finally, Robert Griesemer brought some experience working on the Google V8 engine and also some other languages. So these three together brought out the initial release of Go in 2009, and since then it's grown pretty rapidly in use internally at Google and externally. The TOB index currently has Go at the 13th most popular language. This is up from its low of 122 in May 2015, but down slightly from its peak at number 10 in March 2020. TOB has also given Go the Language of the Year awards in 2009 when it was first released, and 2016, which was around the time when Kubernetes really started to gain popularity. So, I mean, that's great and all, but as I just said, it's actually not the most popular language. It's not very unique since many of its features are already present in other languages as well. So you might ask yourself, why do we actually use Go? So to put it simply, Go addresses issues that were noticed to be affecting developers working at companies like Google. So one of the issues that they've noticed was that when developers were using languages like Java or C++, they had multiple ways to implement similar functionality. And this actually causes a problem because it hides a potential simplicity in the code that is produced. And it makes it slightly harder to reason about the concepts in the code because there's multiple ways essentially that the same thing can be implemented. So Go counters this by trying to, at least philosophically, have one way to do most of the common things that developers need to do. So as we'll see later, for example, Go only has one loop construct and only one way to run things concurrently. And it even has a suggested folder structure as well. And all of these things kind of simplify the process for us. So another time sink at Google at the time was the build process, but also having to test code and optimize it. And I think if any of you have set up a JavaScript build process with Webpack or anything like that by hand, you'll know that it's really tricky to get right, and it can be a huge time sink. So Go fixes this problem by introducing a fully featured toolchain within the language itself. So that means that everything you need to build and test and run your code is all there within the language itself. And it even has a built-in profiler as well. So the next problem happens once you've now tested your code, you've optimized it, you've built it, whatever, you actually need to get it onto a server so that people can use it. And this is a big pain in some other languages as well. So JavaScript or Python, you have to deal with managing dependencies, managing different versions of the language and everything. And it can be a real pain because some unknown issue might cause a dependency to not be available in a specific environment, causing your entire build to fail. As Go is a compiled language, this is a non-issue since all Go programs can compile down into a platform-specific binary, which you can just deploy and run as a program, and you won't have to manage any of the any of the dependencies on the server or anything like that. So all of these problems I just mentioned kind of had a network effect at Google, and what that was that onboarding new joiners took a really long time. So these new joiners had to contend with the cognitive load of understanding things like verbose code bases in languages like C++ or Java, these cryptic build systems I mentioned, yet more systems to handle testing, and then countless tools to evaluate the operation of their software. And then once all of that was ready, they had to then deploy it. And Go tried to really make all of that easier by design and out of the box. So for anyone who's interested in learning a bit more about the rationale behind Go, I'd really recommend the Go at Google talk by Rob Pike. He's one of the language creators. It's definitely worth a watch or a read if you get the time. So another reason to use Go is that it's gaining popularity across the industry. Companies like Google, Netflix, Tesla, Apple, and others have adopted Go already, and many make use of tools that are written in Go, and obviously would have some Go jobs available as well, and the number of Go jobs is also increasing. Many of the fundamental open source cloud computing projects and tools that people use out there, like Docker, Kubernetes, Traffic, are all built with Go as well. As students, we really benefit from these high quality tools being open source because we can use their code bases as a learning tool or simply just as reference. So Go's simplicity relative to these other languages I've mentioned really makes it a uniquely approachable feat to be able to actually go into these code bases and read some code that companies like Google are running in production and actually understand how that code is running in some small part at least. So for anyone who wants to see some great examples of Go in use, I'd really recommend checking out some of these projects on GitHub. So I'd like to go into a bit more of the use cases for Go right now. One of the primary ones is cloud computing. So according to go.dev, 75% of the new cloud native computing foundation projects are written in Go. And some of the big companies like Google, Capital One Bank, and Dropbox are developing their cloud platforms using Go. Another good use case for Go is for any site reliability engineering or DevOps tasks. The usage of Go has really gotten quite popular in this niche. And I think it's probably because a lot of the tools are written in Go, which means that you can write add-ons and things like that for these tools also in Go. And as a result, many of the DevOps people I know love to use Go. The final use case I think is really good for Go is just web development. If you're using it as a backend language or as a full stack tool where you can do server-side rendering of HTML, it's really quite easy. And we'll see a bit later on in this talk how we can create such a server using nothing but the standard library. Okay, so now that we've spoken a bit more about the language and why it came about and where it's being used, I'd like to introduce a bit more of the features. So many of these might be things that you guys already know. Let's start with the basics. And again, you might be familiar with a lot of these concepts already from other languages or things that you've learned. But I'll try to show in each example a way that Go might be doing things a bit differently, which makes it a bit more of a friendly language to use. So it's not going to be an exhaustive list, but for that, I'd really recommend the Go tour or any of the other resources available at go.dev. So Go is a statically typed language, and that means that we need to know the types of variables at compile time. So this little example here shows variables of some different types initialized without a default value. So in other languages, this can lead to unexpected behavior. If we don't give an initial value to these variables, we can't really expect what's going to be in them. But in Go, all variables have default initial values. So if I run this program, we'll see that each of these variables has kind of like a zero type. So for numeric types like ints or floats, this will be 0. For Booleans, this will always be a false value. And for strings, it'll just be an empty string. And that really is a friendly feature for me because you can very easily check for uninitialized variables in this way. Another pain that I've had to personally deal with in programming is having to deal with multiple character sets. And this is especially true if you're dealing with international software. So in Python specifically, dealing with ASCII and UTF-8s, especially in the older versions of Python, was quite painful. In Go, all of the source code and by extension, everything in the language is UTF-8 by default. That means that we can have example programs like what I'm showing you here, where we have characters from different character sets and everything just kind of works as expected. So Go is somewhat between C and Python, and it has some lower features like pointers. Go's pointers are a very similar syntax to C and C++ and other languages similar in that family of languages. But the range of pointer functionality in Go isn't as big. So this is a little example program that shows how we can create pointers. In this case, pointers to integer types. We can then interact with the variables through the pointer, either reading the value or setting the value. And if we run this, you can see that it just works. So as I've mentioned previously, some other languages have many different kinds of loops, but Go only has one. Go only has a for loop. So in this example, you'll see a for loop like you've seen in probably every other language. It's the normal one with like an initializer, a condition, and a post operation. And this just works as you would expect. But in Go, we can actually omit the post operation and the initializer to yield something that looks a bit more like a while loop. But the keyword remains the same. So we can run this and it just also works. And actually the condition itself is also omittable. So we can just leave out everything. And what we're left with is a very basic looking loop, which operates as an infinite loop. And in my opinion, this is a really explicit infinite loop as opposed to some of the others you may have seen. And I think this just really illustrates what I mentioned previously, that Go has this simplicity by design. It might be a very small thing, like only having one loop keyword, but it is trying to remove decisions from the developer and thus reduce our cognitive load. Okay, so another thing that's pretty cool in Go is that we can very easily run things at the end of a function. So Go has a really useful tool called Defer, which lets us schedule things to be run, as I mentioned, when the function containing it exits. So it's quite easy to forget to do this in other languages. You might want to do this when you have an open connection to a database or a WebSocket or something similar, and you need to remember to close that connection. So you can actually quite easily forget this. And in fact, a team I worked with previously ran into a pretty confusing bug, which would cause our servers to crash. And it took us a really long time to debug it, but eventually what we realized was happening was the Linux containers that were running our code on Kubernetes were running into their operating system defined limits on open file handlers. So since everything in Linux is a file, connections are a file too, and thus like our program was basically crashing because we had forgotten to close some connection. So in Go, in production code, you'll often see something like this. So this is a code snippet that I've adapted from some code at work, and we use Go in AWS. And something like this is something you might see very often at the top of our serverless function handlers. So in the first part, we're initializing an AWS monitoring tool called X-Ray. And then right after that, we're deferring its closure. And then after that, we're opening a gRPC client and connection and deferring the connection's closure right after that. So keeping these things together really makes it easier to spot when you've forgotten to do this, and it makes it more explicit in my opinion. Okay, on to the next. So what actually happens in the background when we run defer in Go is that the command that we've deferred is pushed onto a stack, and then that stack will be executed one by one when the function returns. So if I run this little example program, you can see that the first output will be everything in order, but as we've been printing that out, we've also been deferring the calls. So we'd expect that after the done appears, that we start to see everything in reverse order in the deferred prints. And that's exactly the behavior that we see here. So this is the last in, first out behavior of the stack that we can expect. So Go's functions are pretty much like any other statically typed language. So in the previous examples, we've actually already seen some functions. The special function main defines the entry point of a package. It's optional. But if it is present, that's where the entry point will be. This example also implements a little function that just adds two integers. It's not the most useful, but it does illustrate the syntax quite nicely. So we can see that indeed 42 plus 13 is 55. Like Python functions, Go functions can have multiple return values. That means that we can implement something like a swap in one line without having to use a temporary variable like we might need to do in other languages. So running this, we can just see that this can swap to strings. Another important feature of Go functions is that they can also be closures. So in this example, we're actually returning a function from a function. And each of the returned functions will have their own version of the sum variable because of the way closures in Go work. So that means that we can run two different adders and add different values, and the function itself will kind of keep track of the sum for us. So if we run this example, we'll see this behavior. In Go, we can define custom types in a very similar way to what we can in C using the struct keyword. So structs are basically containers with named contents, and they can also have unnamed variables inside them. So they're like a collection of named or unnamed fields. In this case, we've defined like a very simple vertex struct with an X and a Y coordinates. And if we print that out in Go, you'll see a string representation of that. We can add methods to structs like that by adding a special thing called a receiver to a function. So taking our example from before, we can add this function that calculates the absolute value or the norm of this vertex by just specifying the vertex in front of our function. That means that once we have an instance of this struct, we can call the method on that. So now that we have structs and functions, what a lot of other languages do at this point is have interfaces that define a specific set of functions that something should fulfill to be able to be used. So Go implements interfaces like this a little bit differently. In languages like Java, these interfaces need to be explicitly extended on the struct. But in Go, we can kind of leave this away and avoid that boilerplate by just having the struct implicitly fulfill the interface. So any struct that has the necessary functions will fulfill the interface by default. That's another example of kind of where Go removes cognitive load from us, because anyone that's ever seen a Java function inside of a class will know that there's tons and tons of keywords that you need to remember and keep track of to specify exactly the behavior of the interface, basically. So on the topic of removing boilerplates, Go helps us with this in the way it handles importing or exporting values from packages as well. So as I mentioned in Java, there's a whole like list of keywords that you can use for this purpose. But in Go, they aim to just go for a simpler standard, and that's just anything that's capitalized will be exported, and anything that's uncapitalized won't be. So this example shows that behavior. The local variable, since it's got a lowercase first letter, won't be exported by this package, but we can see that the math standard library has an exported constant pi with a capital P. So that means that we can access it from other packages like this main one that we have here. Cool. So now that we've got the basics down, I'd like to go a bit more into some useful features that we might see in industry. So one of the biggest ones these days is concurrency. So to begin with, I'll just quote a bit from an MIT web development class, 6005, which introduces the topic of concurrency. So they say that concurrency means multiple computations are happening at the same time. And this happens a lot of places in modern programming. So multiple computers in a network, or multiple applications running on one computer, or even multiple processes running together in one computer. So it's actually pretty essential in a lot of use cases. For example, websites need to be able to handle multiple simultaneous users. Mobile apps might need to run some code to execute something on a server in the background, and certain graphical user interface applications, like an IDE, for example, need to be able to do things in the background, like compile your code while you're still editing. So all of these features require concurrency, and this is another topic that gets really difficult in certain languages. I'm going to show you some features in Go, specifically these four, and how they kind of make it easy to implement concurrency as opposed to these other languages. So the first thing to talk about with concurrency in Go is the concept of a Go routine. And a Go routine is basically a very lightweight operating system thread. And all of Go routines in the same program have access to the same memory space. But these Go routines get scheduled by a special scheduler that runs in the background called the Go Runtime Scheduler. If we want to use Go routines in our programs, it's really simple. All we have to do is add the Go keyword in front of any function that we're calling, and that will be run in its own Go routine. So in this example, we're basically just looping and sleeping in each loop and printing out a string. And in our main function, we're running two versions of this function, one in a Go routine and one in the main thread. And if I run this, you'll see that there's kind of like a random order to the outputs. And that just has to do with how the Go scheduler actually runs these things in the background. That's a pretty complex topic, so we won't go into that today, but it's also really interesting. So I'd encourage you to read about that if you're interested. So once there's multiple things running in your program, inevitably you need to be able to get some data from one of the things that's running, or communicate between them, or send signals around. And this again is another really tricky thing to do. But in Go, they have a really simple construct called a channel that enables this communication between things that are running at the same time. We can think of channels almost like variables. They have a type, and they also have the ability to send and receive data. And these channels really make it easier to take a large task and break it down into smaller constituent tasks. So if we have a larger task and we want to break it down, we can do that with the help of channels and Go routines. So in this example program, in our main function, we have a list of integers, and we can imagine that this might be a much longer list in real life. So what we're doing here is we're making an integer channel, and then we're running two different Go routines, each executing a half of the channel, a half of the array, sorry. And then once we've initialized both of these Go routines, we're waiting for each of them to finish and assigning their results to a variable. So this really helps us kind of do a map reduce type of process where we break up a big task into smaller ones and then combine the results further down the line. So if we run this, we can see that it calculated the sums of both of the halves of the array and then the full sum at the end. So another problem that you might run into when you have multiple things running at the same time is keeping track and making sure that everything gets a chance to finish. Just a second, please. So in the previous example, we just used the channel operator to assign the values to variables, but sometimes the situation is a bit more complex than that. So Go has a construct called a wait group, which allows us to ensure that everything has a chance to finish. So in this example, we're basically adding 1 to the wait group's counter every time we start a Go routine. And then at the end of the function, we're just waiting for the wait group. And that will ensure that all of the different Go routines you have running have a chance to finish before the function returns. So if we run this, we can see that each of the worker functions started again in a kind of a random order, and each of them also had a chance to finish. So the final problem that I want to talk about with concurrency is you might have to access shared data, and especially in Go, this is true since all the Go routines have a shared memory space. So what might happen is that two different things try to access the same variable and let's say write its value at the same time, and that can cause some pretty nasty issues like race conditions, etc. Go includes a construct called a mutex or a lock in its sync library, which allows us to basically make these things thread safe. So we can basically look at an example program like this, and every time we're accessing the shared value, which in this case is a map, we're locking and unlocking it. So we're locking it before, doing our necessary work, and then unlocking it. And Go is smart enough that if a Go routine finds a lock, it'll just wait and be scheduled later down the line so that it'll hopefully find the resource that it's trying to access in an unlocked state where it will then be able to do its work. So if I run this example, we'll see that each of the 1,000 Go routines for starting here is able to access the shared memory and increment it. So we'll get 1,000 for the value at the end. Cool. So another thing that I really appreciate as Go is when you join a new team or start working on a new project, it can be a bit daunting because it's usually like a really big code base and you're left on your own to just kind of understand how things work and where everything is. And this whole process is usually helped by documentation, but unfortunately, helpful documentation is also pretty rare. So a pretty nice feature of Go is that we can use comments to automatically generate documentation for our projects. These comments just have to follow like a pretty basic standard, but it's quite easy to keep track of. So this is a real world example I've pulled out of an open source project called Trivy. They're a tool that scans software for vulnerabilities and helps developers ensure that those vulnerabilities can be fixed up. And this is an example of a status configuration in enum that they have in their code base. And you can see that each of these things has a very specific commenting style, where the name is the first part. And then after that, we have a short description on what it is. I have a little example that I've set up. So this is an example package, and I'm showing you different versions of these comments, like for functions, constants, custom types, and even for the package itself. And you can use the Go command line tool to generate a documentation site from this. So we'll see that now. So here I'm just running a make command that runs GoDoc, and we'll have a website that pops up that looks something like this. So here you can see our entire package is documented. It's interactive. We can jump through different examples, and it'll show all those comments that we had in a nice readable form here. So it's going into some code that we might look at later. But yeah, it's really helpful, especially on big code bases, to be able to generate documentation like this by just running this command. So another cool feature that Go has is the ability to generate code. So a lot of our work as developers is actually pretty repetitive, and especially things like writing CRUD operations and things like that can get pretty tedious. But Go has some pretty cool built-in tools that help us automate repetitive situations like that. So let's assume we have a situation where we have a struct representing a person, and it might have some methods on it, allowing us to print the person's name and age or something like that. And let's assume that our project is to create many of these structs to represent many different things. And for each one, we'd also like to have a special type representing a list of that type. So we could, of course, write all of this by hand, but instead we could opt to only write the basic types ourselves and then generate the list types. So if we wanted to do that, we could set up something like this shell script in this case that I've done, which basically just acts as a template. And we can access this from our Go code by just writing Go generate in a comment and then accessing the script. So if we run this in the example I'll show you here, in the IDE itself, it's picking up that this can be generated, and I can just click on that and it generates the function for me. So here's the generated code that was the result of that. So you can see we now have a person list with the filter method as well. So this type of code generation is really helpful, and it's used quite extensively by projects like Kubernetes as well to generate code that might be quite repetitive and tedious to write by hand. Another really cool feature that Go has is the ability to access any C code. So within C, you can just add the C code right there, and you'd be able to interface with it. So there's a pretty good blog. It's a pretty old one, but it's from around the time where C Go came out by Andrew Charand, and I'd recommend that you check that out if you're interested in using C and Go together. C Go also makes use of comments. So basically what you do is you can paste in some C code as a comment into your code, and then make sure that it's right above an import, a special import called import C. And then in your Go code, you'll be able to access any of that C code with that imported C namespace. So in this example, we're just having an example function that returns 42, and if we run it in Go, we can see it still returns 42. Cool, so that's kind of it for the explanation part of this talk. I'll jump over to some short demonstrations now. So the first one is an example from the Go tour where they ask us to essentially write some code to determine whether two binary trees are equal. So they give us a binary tree struct already, which has left and right subtrees, and each tree node has a value. And they're asking us to implement the following method. The exercise is to implement a function that walks through the tree, and then a function that uses the walking function to check if two trees are the same or not. So I've already set this up as examples just to help myself along. So this is the code that the Go tour provides us with. It just has two function signatures, and we need to kind of flesh this out. So if I switch to my next branch, we'll see that here I've added an implementation for walk. So this just basically checks if there is a left subtree, we walk through that. And if there's a right subtree, we walk through that. And in each case, we're using a channel to return the values. Switching to the next branch, we can see that in the main here, I've added some code that we can now run. just to see that our walk function actually works. So if I just go into package tree and I run go run tree.go, we can see that I have a tree of length 5, and the tree package they provided us with generates random values. So it's just walked through the 5 values and printed them all out for me. So if I now switch to the next branch, what I've done here is to add some helper code. So the one is just using a walk to walk through something and then close the channel when you're done. And I'm actually using that to implement a length function, which just determines how long a tree is, because we might not know that in advance. Which finally lets us do the last step, which is to implement the same function. So the first thing I'm doing is checking the length of both of the trees. If the trees are not the same length, we can safely say that they're not going to be equal. So I'm just returning false. In the case that they aren't, I'm creating 2 channels and then basically just looping through the walk of each tree and ensuring that the values coming from the channels at each point are the same. So the trees will be walked in the same way, and at each point, the tree node will return its value through the channel. And if they're the same tree, each of those responses should be exactly the same. So we're just checking if that isn't the case, we are short-circuiting to returning false. And then if we've gone through the whole loop and we've never had to return false, we just return true because they'll be equal. So we can now run this example using the command. So go run command tree main.go, and we can see that the 2 trees here, which just generated 2 1 node length trees, are in fact equal. The next exercise I wanted to go through would just be something that I mentioned at the beginning of the talk, and that's that we can actually create a whole web server using nothing more than the standard library. Switch to my first web server branch. So we can see I've done all of this up here in command. So let's assume we have the following HTML. This might be a whole website, but we want to use Go to serve this HTML. So what we can do is just write a very simple Go command, which uses the built-in file server provided by the HTTP library. We point it at the folder containing our HTML, and then we can create a handler function, which will interact with the file server at the following endpoints. We can turn this into a fully fledged web server by also exposing a port. We can use the built-in listen and serve function for this. So if I run this now and switch over to sharing my Chrome. Okay. So the server is running. We can see that we have our basic HTML and it's working. So in just a few lines, we were able to take our HTML and serve it in a pretty safe way using Go. But yeah, at this point, I'd like to welcome any questions and any suggestions, things that you guys might want to say, but also just want to thank you for taking part. So Veronica, to answer your question, I think it's a pretty good language to learn as maybe a second language. But to be honest, it's although the syntax might look a bit challenging, it's really similar to JavaScript or Python. If you take a look at it and you actually use it, the functionality is pretty much the same, and the same concepts that you learn in those languages will apply in Go as well. It's just that Go, as opposed to JavaScript or Python, is also statically typed and compiled, so it's a lot faster and a lot more versatile than those languages. Python and Go are great. Python's my favorite language, but I'm really starting to like Go a lot as well, just because it offers like kind of a best of both worlds approach, where you can still write code that's simple enough, but really benefit from sort of the more heavy lifting features that other languages might have. Also interested in the AI and data science part myself. So Go is actually being used to do some machine learning engineering work. So at Google, a lot of the TensorFlow models and things like that will be served by Go servers. So it's not really directly linked to work in AI, but a lot of the infrastructure like data pipelines and things like that, and things that are actually deploying the models into production will be written in Go. So I hope that answers your question. Doesn't look like it, so I want to just say thank you everyone for attending, and I guess that's the end of the presentation. I hope you all have a wonderful week.